Okay. All right. So we'll, I guess we'll get started. You guys took the midterm exam on Wednesday, and then I'm going to meet with my TAs and graders immediately after this class to grade. So I haven't looked at it at all, so I don't know how you guys are doing. But we'll find out in a few hours, and I'll put your grades online and whatnot. But I don't know. Of course, I think so, but I tried to make the exam fair in terms of like what I told you to expect and what was on there. But of course, that's my opinion. All right, so let's see. What do we? I don't have. These are just old slides from before, but today I thought we would take a look at the MNIST Handwritten Digit Database. Okay, this is it's almost like a classic data set now. As far as image recognition goes. And we're going to use a neural network to program our, or to make predictions on the handwritten digits, okay? Let me see if I have actually some really old slides from previous quarter. Let's see if this is the one. Okay, this is a little bit of what I guess we'll be doing. So the MNIST database, you can just type in. Should be one of the first hits. MNIST dataset. Okay, this is the official one. Like people on Kaggle and different websites around the internet have taken this and kind of like turned them into CSV files and things like that, which is fine. But the original data comes in these 4 files. Okay, and so this is the original data set. You'll download these, put them into a folder, probably called MNIST, somewhere on your hard drive, and it comes with 70,000 labeled images, okay, or 70,000 things. 60,000 go into training, 10,000 go into testing, okay, and each of these things is you'll have these little images, okay, of basically some handwritten digits, okay? They are 28 by 28, okay? They're tiny little images, 28 by 28, and each pixel is black and white, going on a scale from 0 to 255, okay? So I guess 8 bits to store a color value, okay? From 0 to 255, where it forms some kind of thing, all right? And this was kind of prompted back. I don't know when it was prompted, but back when they were trying to optimize or improve things at the post office, okay? Because before, people would manually sort. They would look at the address on the thing, they would look at the zip code, and they would put these zip codes go over into this bin, these zip codes go into this bin, so on and so forth. And they wanted a machine to be able to do this. And in order to do that, the machine would have to be able to recognize digits And a lot of people handwrite addresses, right? Probably anytime you send I don't know how often you send a letter, but when you do, you probably have to write the address by hand, okay? Unless it's like a pre-labeled envelope where you're returning a bill or something. So anyway, this is the problem, and so each of these digits are, they have a whole bunch of these examples that are labeled, and they're just tiny little 28 by 28 images, and we want to be able to say, oh yeah, this is a number 4, this is a number 5. Some people's handwriting is bad, right? Like this is a number 5, I guess. And people have different stylistic things, like this is a 9, even though it looks like a G, and I guess this is a 7, but anyway, this is what our data looks like, okay? And so when we set up, what we're going to do is we're going to set up a neural network so that our input is going to be this 28 by 28 image, and our output is going to be a classification, okay? It's going to be either a 0 or a 1 or a 2 or a 9, okay? One of the 10 digits. So this is a little bit different from the one where we were trying to predict the test score. We said like hours of sleep and hours of study, and you go through the network and we predict the test score. That's considered a regression problem because the value you're trying to predict is a numeric or a continuous variable. Okay. Now we have a classification problem. Oh, ran out of battery. Now we have a classification problem, and we need to predict, one of 0 through 9. Okay, and so what we do is we're going to take this image that's 28 by 28, and we're going to basically just unroll it, or just unstack the thing. So it's a vector of 784 values. Okay, so we take this thing, 28 by 28, we turn it into just 784 values, and that's going to be basically our input x. So our x matrix is 60,000 by 784, okay? And arbitrarily, I just chose 30 nodes in our hidden layer, okay? So we have, every single one of these nodes connects to every single node in the next layer, okay? So you got all of these connections going from all 784 to 30. So your first weight matrix has a lot of values. 784 times 30, so what's that? That's 20-something thousand connections? No. Yes. Yeah, 20-something thousand connections, okay? In the first weight matrix, okay? And then our output layer is going to have 10 nodes. Okay, we're going to have a node for 0, a node for 1, a node for 2, all the way up to a node for 9. And the way we encode our training data is that if the digit is currently labeled a 5, the answer that we want it to predict once it goes through the thing is we want it to be 0 for everything, and a 1 for the 5, and a 0 for everything else. Okay, so that's how we're going to train it. We're going to say, here's your input. Here's this image, which is 784 values. After it goes through the network, what we want you to output is a bunch of zeros with a 1 at 5 and a bunch of zeros everywhere else. Okay? Now our neural network, it doesn't produce zeros and ones. It produces values between 0 and 1. So it can produce like values like 0.01, 0.99, 0.5, things like that. Okay? And basically, we're going to just penalize any error, right? So if it predicts 0 and it should be a 1, it's going to have a penalty. And if it predicts like 0.7 and it should be 0, it's going to have a penalty. So our loss function is basically how off our vector of kind of predictions are. And so, this is what we want. We want zeros and ones, and we would be satisfied if we get something like 0.001, 0.001, 0.001, 00, 0.999, 0.001, and so on and so forth, okay? That's basically what we're kind of aiming for. And so for that, we're going to basically do our neural network stuff, okay? And so it's much like this, just with a bunch more nodes, okay? 784, 30, and 10, and we went through the process, and basically all of the work we did for backpropagation in matrix notation still applies here, okay? All we've done is we've just changed the dimensions of our gradients, okay? So when we want to do gradient descent, we needed the gradient here. This thing is going to be 784 by 30 rather than 2 by 3, okay? And then this thing is going to be 30 by 10 rather than 3 by 1, okay? But it still works. Everything, all of this stuff that's in matrix notation still holds up, because by working in matrix notation, you just kind of modify things a little bit so that the dimensions remain aligned, okay? And so this will generalize, instead of being 2 by 3 in the end, it's going to be 784 by 30, okay? So those are going to be the things that change, and we code it up, okay? And so we'll do this. The code looks very similar to what we had before. Before that, I have to load a little bit of code to try to load our data files, okay? And so so this is a function that someone wrote in order to get us to load our data. Let me just set my working directory. Oops, no, not here. Okay, so so all this does is it just reads in the data, because the data is in these kind of funny, I don't know, IDX1 ubyte files, okay, which is a little odd. So so anyway, you load this up. This is from Brendan O'Connor, so thank you, Brendan. And I'll go ahead and just run the function to load it. Takes a little bit to load because there's a lot of images, and we can see these. It takes up quite a bit of space in memory. Okay, we've got 179.7 megabytes, and then if we just look at the structure of, say, the training data, okay, it comes. It's a list of 3. Okay, one is just how many images we have, 60,000. And then the first is a big matrix. Okay, train $x is a big matrix, 60,000 rows, 784 columns. Okay, each row represents one image. And so, so let me just kind of just show you. So here is j equals 2, and is this text big enough? Can you guys see that? Kind of. All right. If you squint. Okay, so the training label says this is the image 0. And here if I have it be displayed, 1, 2, 3, 4, 5, 6. You can see it's just a vector, okay, of 784 values. I wonder, can I, all right, let's see. Let's see if I can get this right. If I resize my screen, oh, okay, we're almost there. There we go. Okay, so here I've got 28 columns across, and I guess 28 rows now. And so you can see, because there's there's kind of a natural thing where it's like the 0 only takes up 1 digit, and then when it's a dark spot, a dark pixel, it's going to have like a number like 250, which takes up 3 digits. And so just naturally, it kind of looks like a number, right? So if I change this to like j equals like a different row, and I say, let's look at that. Okay, that looks kind of like the number 4 and whatever. Okay. So anyway, but again, the computer doesn't see it like this. Okay, it doesn't have eyes the way we do. Okay, and all it's seeing is just a big vector, right? Like it's just seeing a row of 784 numbers. So it doesn't get the benefit of our eyes. I'm going to make our text bigger for you guys. Okay, is that better? All right. Okay, so anyway, that's just taking a look at one of these vectors which has 784 values in it. Here I'm going to take, I write a function called vectorize, and basically it just takes a label. So like if I put in the number 5, it's going to turn it into rows, a row of 0 and 1s, okay? So basically it just starts off with a bunch of zeros, and then it's going to replace the digit in the j plus 1 position with a 1, okay? So 0 will fill in the first column, and then the last column, the 10th column, 10th value in the thing will be for 9, okay? So it's, we're offset by 1, okay? So I create a function called vectorize to do that, and then I use the apply to take all of our training y labels, okay? The train $y is the true encoding, but we're going to turn all of this into kind of vectorized things, okay? So if we take a look at the result is that now we have a matrix y of that's 60,000 rows and 10 columns wide, okay? And it's turned digits like 5 into, changing this number. The next one is a 0, and so it puts a 1 in the 0 column, and a 4. The next one's a 4, so it puts a 1 in this column. Okay, so that's all I've done, because this is what we want it to predict. We put in a row of 784. We want it to go through the network, and we want it to output something that looks like a bunch of 0s and 1s, okay, or at least something close to it. Okay, so yes, question.
Are the numbers in order in the rows? Like 0, 1, 2, 3, 4, 5, 6, 7?
So yeah, so the first column is 0, and then the last column corresponds to 9.
No, the data set, the training data.
In the training data?
Yeah.
Oh, in the training data, it's not in any order. It goes 5, 0, 4, 1, 9, 2. Okay, so if we look at if we look at the first data thing, it's currently labeled a 5, and we can plot it, and this is what the image looks like. Okay, if I do the next image, that's labeled a 0. If I do the next image, it's labeled a 4. Okay, so that's a 4. The next one is a 1, which looks like that. The next one is a 9. Okay, and so these are the input things, and this is what it looks like. But again, the computer only sees just a vector of 784. Okay, so anyway, we'll go ahead and just start writing up what we need in order to perform gradient descent for our neural network. Okay, so I've got the sigmoid function, the derivative of the sigmoid function, the cost function. Okay, and then I'm using And I don't know if you remembered the code I showed on Monday where I created a neural network, but I kept these as kind of variables. So the input layer has 784 nodes, the output layer has 10 nodes, and then the hidden layer has 30 nodes, okay? And that hidden layer is arbitrarily chosen to be 30. You can choose to have 100, or you could choose to have, you know, more or less. I arbitrarily chose 30, okay? I start off with, I have two matrices, weight 1 and weight 2, W1 and W2, and so it's just a matrix. Weight 1 has 784 rows and 30 columns, hidden layer, and then weight 2 has 30 rows and 10 columns, okay? And then to initialize, I'm going to arbitrarily pick or randomly select values between negative 0.5 and plus 0.5. So I just do runif, which generates values from 0 to 1, and I ask it to generate whatever 784 times 30 is, and then I subtract off 0.5 to kind of just offset it so it has some both positive and negative values, okay? So I'll go ahead and I do that, and so now I have, we can see over here, I've got my weight 1 and weight 2 matrix, okay? 784 by 30, 30 by 10, okay? Okay, and then we could go ahead and just jump in and start training, okay? One thing though is that I have 60,000 rows, okay? 60,000 rows is a lot, and you know, if we look at how do we calculate one of the gradients, you know, we're gonna have to do things like x transpose times y minus y hat, and this is going to be something like 784 by 60,000, okay? And doing some computations will be kind of fairly expensive for the computer to do, to try to do all 60,000 rows all at once. So what we're going to do is we're going to just do a what we call stochastic gradient descent, okay? And what stochastic gradient descent does is it says, okay, let's not do all 60,000. Let's just randomly select a handful, all right? And so I've arbitrarily chosen 10, a batch size of 10. Some people might say let's do 100 or whatever. Again, this is arbitrarily chosen right now. But we're going to do, I'm going to just randomly select 10 rows. Or actually what I'm going to do is I'm taking 60,000 and I'm going to shuffle 60,000 values. And then I'm going to just take the first 10 and then the next 10 and the next 10 and the next 10. Okay? So that's what I'm going to do. So here I sample 1 through 60,000, which is okay. So I just shuffle up 1 through 60,000, and then I create a sequence that says that goes 1, 11, 21, 31, so on and so forth, all the way up to 59,991. Okay, so I've got 6,000 kind of little batches of 10, and right now, and then I set a learning rate. Okay, and then so. You know, for I in JSub, which is the vector 1, 11, 21, 31, up to 59,991, we're going to just select the index from I to basically 10, or I to, you know, 10 more than that. So, so we do that. We subset our training to X. Likewise, and we subset our y, okay, that way, to use our kind of our training labels, our vectorized training labels. And then we figure out what our y hat is, given our current weight matrices. So I just do forward feed. I do x times our first weight matrix. I apply the sigmoid function to it, and I get A2. I multiply A2 by our second weight matrix, and I apply the sigmoid function to that, and I get y hat. Okay, so this is exactly what we were doing before, which is I guess it's a different set of notebooks. Okay, so this is what we have. You know, x times w is z2, f of z2, or the sigmoid applied to z2 is a2, a2 times w2 is z3, and then the sigmoid applied to z3 is y hat. Okay, that's all that's going on right here. Okay, x times w is z2, sigmoid of z2 is a2, a2 times w2 is z3, sigmoid of z3 is y hat. Okay, then we calculate our gradients, which we did. We had a lot of work to do, a lot of calculus to get to that point, but we got it. Okay, we found our gradient to be this: a2 transpose times negative y minus y hat element-wise multiplication with f prime of z3. Okay, so delta 3 is this thing minus y hat times f prime or sigmoid prime of z3, and then dj with respect to w2 is a2 transpose times delta 3, a2 transpose times delta 3. Okay, and then the other gradient after we did all of our work is this, where delta 2 is delta 3 times w2 transpose element-wise multiplication with sigmoid prime or f prime of z2. Okay, so delta 2 is delta 3 times w2 transpose times sigmoid prime of z2. So we have matrix multiplication and element-wise multiplication. And then we for our gradient dj with respect to w1, we do x transpose times delta 2. Okay, x transpose times delta 2. So it's exactly what we've done the math for to get. All right. So so this is our loop. Figure out what our y hat is. Figure out what our gradients are, because our gradients require the use of y hat. And then once you figure out your gradients, you update your weights by doing your current value minus your gamma or your scalar value multiplied by the gradient. Okay, so that's gradient descent. Take where you are, subtract off some scaling factor times the gradient, so you're taking a step downhill. Okay, and so that's it. Okay, and I just do for I in 1 through I don't know, whatever this sequence is, 6,000 things, and I'll just go ahead and I'll just run through it. I must not have run all of this code earlier. Okay, and then we'll go ahead and we'll run this. So it takes a few seconds to run. Okay, so it's running right now. It's going 10 at a time, going through all 60,000. Okay, and now it's done. And so I've just gone through. Okay, felt like I was gonna. That was disappointing, but okay. So I've run through all 60,000 rows just one time, but just 10 at a time. Okay, so I did 10 at a time, 6,000 iterations. I've basically just gone through the training data once. I could, if I wanted to, go back and start up here and do the whole thing again and continue to update my things, but I think we get pretty good results just even after running through the training data just once. Okay, I tried this out earlier. Okay, so now I want to kind of test the performance. Okay, so I'm going to go to the test data set. Okay, and there's 10,000 rows in the test data set. You know what? I guess we'll go ahead and let's do all 10,000. Okay. So I'm going to take all 10,000 rows in our data set. I'm scaling it down so that their values between 0 and 1, because I think that's what I did to train it earlier. And so my batch size is 10,000. Okay, and I'm just going to go ahead and run through this. This will take this. Luckily, we're using matrix multiplication, so I just take our test data and I do forward feed using our current weight matrices. So we've already done all of the training, okay, or at least one full kind of round of training where I've got some weight matrices, W1 and W2, and I'm going to just take all of my test data, which has 10,000 rows, and just run it forward feed through the using our current weight matrices that have been trained. So I do Z2, apply the sigmoid function, multiply A2 by W2, and I apply the sigmoid function again, okay? So our guess, if we take a look, let me just do y underscore hat, let's just look at like the first row, okay? If you look at the first row, it looks like this. It looks like this, which is hard to understand. So I'm gonna just go ahead and just round this off to like 3 decimal places so you guys can see. And it looks kind of like this. So we get 0, 0, 0.13, 0, 0, 0, 0, 1, 0, 0, okay? So this would correspond, so each column corresponds to one of the digits, right? So this is 0, 1, 2, 3, 4, 5, 6, 7, okay? So this is a 7, 8, or 9, okay? So this means it's predicting 7. Not all of the columns, or not all of the training rows are as clean cut, okay? So this one, the largest value is 0.993. The next row is 0.99. So I mean, this is doing pretty good. Some of the rows don't do so great, okay? But basically what I'm gonna do is, I'm gonna take one of these things. This one, let's just go back to that first row. You can ask max column, okay? You can say which element, it works for matrices, okay? Okay, so if I did like the first 2 rows, okay, it looks like this. We have the largest value is in the 8th column, and then in the second row, the largest value is in the 3rd column. So max column will tell you like what's the largest value in each row, okay? So I'm gonna do max column, but remember it's offset by 1, so the guess that we're gonna do will be the max column minus 1, okay? So I go ahead and I do that, and this is our guess. And so the results is I'm going to take our guesses and compare them to the actual test labels, okay? And so, so the head of my results looks like this. So this is our guess, and then the true test label is taken from test $y. They're already labeled for us, and we can see, at least for the first 6, we got them all right, okay? All right, and so I can table the results to see just kind of how we did, okay? And this is what we get, all right? When it was 0, I forget which way it goes. But basically, the diagonal is where it got it right, and then the off diagonals are where it got it wrong, okay? So when it was 0, it got 0 953 times, and I don't know which one. I'm not sure which way it goes. But basically, it either guessed the number 2 when it was 0 6 times, or it guessed the number 5 when it was 0 14 times, or it was a 5 and it guessed 0 14 times. Okay, something like that, okay? And so our accuracy is I'm going to just take the sum of the diagonals and divide by 10,000. So we had 10,000 test cases, and I'll just do the sum of the diagonals divided by 10,000. And we've achieved around 92, 93% accuracy just with our, I think, fairly simple neural network where we have 30 nodes in our hidden layer, okay? We just have 30 nodes in our hidden layer. I don't think I used anything fancy, right? This is how we trained our neural network, just using the calculus we did, which was, honestly a little bit of a pain to work through. And then we just used simple gradient descent, okay? So this is kind of your most basic neural network, but it has, 93% on recognizing a vector of 784 values into a digit, I think is pretty good, okay? And we can further improve it, or at least reduce our training error by, I could just run through the entire training set. So far I only ran it once, but I could just run it like for another, we might call it an epoch, okay? And I'll just allow the training values to improve, and I'll probably get a little bit of incremental improvement here. Did I do something that I didn't want to do? I think I've changed my batch size, yeah. All right. Now I'm doing batch sizes of 10,000 rather than 10. I regret my decision. Oh dear. Okay. Yes. Sorry. Okay. Well, that's why we'd use a batch size that's not 10,000. Okay. Oh, all of my data is lost. Okay. Well, it was fun while it lasted. All right, well, we got 93%, 92.5% accuracy. And then basically I was going to show you like the times where it misclassified the thing. And when you see the mistakes that the thing makes, it's like forgivable, right? You're like, okay, I understand why the computer didn't guess this, because this person has terrible handwriting. Some of them it should have gotten right, but you know, you look at it and you're like, oh yeah, I can understand. I also I've uploaded this onto CCLE, and there's an extra chunk of code here that works to do the numeric gradient, right? So we did all of that calculus, and you guys have accepted my work as being true or correct. No one really questioned me, but there's a lot of like some weird stuff going on there, right? Like who does element-wise multiplication? That's not something that exists in linear algebra, but we kind of do it for this stuff. So there's questions of like, is our gradient even calculated correctly? And so here we do numeric gradient checking by setting your initial gradient matrix, okay? Or I'm sorry, not gradient, weight matrix, and then you add a little perturbation. You just add 0.0001 to it, see how much the result changes, and then you kind of compare that to how big you changed it, and so you can figure out your numeric gradient for W1 and your numeric gradient for W2, and when you do it, it works out to be quite similar. Okay. I guess we don't have this. Okay. I guess that's that. I don't know. I don't feel like running everything again after the thing crashed. But anyway, all to say, even a simple neural network design, okay, this is about as simple as we can make a network. We just have a bunch of nodes, one hidden layer, and then some output nodes. We get some fairly good prediction accuracy. All right. I'm finishing up the homework assignment where you'll basically be doing this, but for kind of the classic iris data set, and you'll classify it into one of the 3 species. And so you have that to look forward to, and I don't know. I hope this is kind of neat. Again, this is about as deep as we'll get for neural networks. You can do a whole lot more. They get a lot more complicated and a lot more powerful and exciting as well. But we'll end here. Have a good weekend, and we'll see you guys on Monday.